When a conductor moves through a magnetic field, a current can be induced in the wire. The figures below show one or more metal wires sliding along fixed metal rails in a magnetic field. So all the bold lines are conducting materials. We want to determine if there will be an induced current. Would it flow clockwise or counterclockwise? Sometimes we'll just get a brief transitory charge separation. Sometimes we'll get a complete current in a loop. If we look at letter A here, we see that there isn't a complete circuit created. So current can't continuously flow in this situation, but we could have charge separation. What we want to do is we want to use the right-hand rule to determine what the direction of forces will be on the particles in that moving wire. The way it works is you point your pointer finger in the direction of velocity, and then your middle finger has to point out of the page in the direction of the magnetic field. There will be some other fingers involved here. And we see that the thumb points to the right in this case. So the pointer finger is the velocity of the wire. The middle finger is the magnetic field direction. And the result will be the force. Now this will be the force on positive particles. What this does is it makes positive charges in the wire want to move to the right, and negative charges in the wire would want to move to the left. Here's a close-up view of what's happening inside the wire itself. Positive particles will be pushed to the right. This shows us that there will be a conventional current to the right for a brief time, and it'll create a charge separation. So that this side of the setup becomes net positively charged, and the other side of the setup is net negatively charged. So this picture shows what would happen in that wire when it first starts to move. But over time, what we would have is simply polarization. So this would be after the charges rearrange. The magnetic force on the positive particles will hold them on the right side, and it'll hold the negative particles on the left side. So there'll be an initial rearrangement. For setup B, though, we see that we do have a closed loop. Let's use the right-hand rule on this wire. In this case, the velocity of the bar is to the left, The magnetic field is into the page. And the thumb points down. So the magnetic force on positive particles is going to be in the downward direction. What this is going to do is it's going to induce a current in the loop overall. And as long as the bar continues to move, there will be current flowing clockwise in this loop. So positive charges will feel pushed this way. That's the idea. So in this first example, there's no complete circuit. So current is 0 as time goes on. But in this second example, we will have a clockwise current. What about in the case of C? Here we see that the velocity of the movable bar is 180 degrees opposite of the magnetic field. So there actually won't be any force according to the right-hand rule and the cross product rule. For that reason, the current is 0. In the case of D, we have all 3 bars moving. We can do a right-hand rule on each one individually and see which direction it causes positive charges to want to move. For this upper left bar, we would have this situation. The velocity of the bar is toward the upper left. The B field is out of the page. Therefore, positive charges will feel a magnetic force that's directed up. So when those charges are pushed in that direction, that is current. We can try it at other positions as well. Again, we find that the magnetic force will be in a clockwise orientation for these charges. And if you do the right-hand rule on this segment, you'll see the same thing is going to happen. So simply by the loop expanding here, it's going to create clockwise current. So I is clockwise. The induced current is clockwise in this situation. This is an interesting one. What if these two bars are moving while the left and right bars are stationary? The bars are moving upward. The magnetic field is directed into the page. And the force on the positive particles is going to be directed to the left. And that's going to be the same for both the top and bottom bars. So positive charges are pushed to the left for the top bar. That's going to create an accumulation of positive charge on this side of the object. And we'll have negative charge on the other side. But the same thing is going to happen down here as well. There'll be a charge separation, a polarization of the object. Now the magnetic force is what keeps these charges separated. But the magnitude of charge at this point is going to be by symmetry the same as the magnitude of charge at this point. So is there really any reason for current to flow between the top and bottom wires? And the answer is actually no. So even though there'll be this initial transitory rearrangement of the charges, there won't be a current as time goes on. There'll be an initial rearrangement of the charges, but the current is zero after that. What about this situation? We've got a loop, so there could be a current if the conditions were right. And half of our loop is in a magnetic field, but this wire is in a place where the magnetic field is zero. So what will happen in this situation? Because there's no magnetic field for the wire to move through, there won't be a magnetic force. And therefore, there won't be any induced current. Now, even though I just solved all these problems using the right-hand rule, I also want to solve them using a new method. It has to do with the area of a loop and the flux through that loop. It's an alternative way of determining what the direction of current will be. We'll see shortly that the formula that governs this situation is epsilon equals negative change in magnetic flux divided by the change in time. Now the magnetic flux, as we saw in the past, was B times A times cosine of theta. And this just shows that there's several ways that the flux can change. There could be a change in magnetic field, or a change in a loop's area, or a change in the angle that the field makes with that area. In all of these problems, we're mainly dealing with this type. We want to ask ourselves, is the area of a loop changing? Because if it is, then what will happen is there will be an induced electric potential, which could cause a current. The top formula is for complete loops. But when we have just straight wires, we can use the formula epsilon equals B times L times V. Now in this first situation A, we see that there is no complete loop. So we can't say that the area is changing because we don't even have a loop with which to calculate an area. The magnetic field is certainly not changing, and there's no angle to change either. What we have in this situation is a moving straight wire. And so what it would do is it would induce a voltage equal to BLV, where B is the strength of the magnetic field, L is the length of the wire, and V is, of course, the velocity of the wire. When a potential difference is created, we use the right-hand rule to decide which side gets the positive charge and which side gets the negative charge. But there won't be a current in that case. In B, we see that there is a complete loop. And we can look at the area and how it's shrinking. So the area A of the loop is decreasing. According to the law above, this means that there will be an induced voltage. Positive charges will be pushed downward, negative charges will be pushed upward, and so that's going to make a current flow. In the case of C, we do have an area that's decreasing. But the initial magnetic flux of the loop is 0. And the final magnetic flux of the loop is also 0. For this reason, no current will flow. In this problem here, we see that the area is increasing. So the magnetic flux through the loop is also increasing. Since the flux is changing with time, there will be an induced voltage which will create a current. Now check out this problem. Is the area really changing? No. Even though both of the wires are moving, the distance between them would stay the same as long as they have the same velocity. And if A doesn't change and B doesn't change and the theta between them doesn't change, then that means that the magnetic flux is not changing. Therefore, no current will flow. But keep in mind, we still will have a charge separation according to epsilon equals B times L times V. So we'll end up with a positive potential on the left side of the object and a negative potential on the right side. The positives and negatives can't come back together because they're feeling magnetic forces keeping them separate. If the motion stops, then they will be able to come back together. In this problem, we see that the area of the loop technically is changing. But is the flux really changing? Well, the initial magnetic flux is really due to the field that's in this portion of the loop. And even if the wire moves up, that amount of flux is really not going to change. So the magnetic flux here is actually constant. And for that reason, current will not flow. And in this case, there's not even going to be a potential difference across the wire because it's not even moving in a magnetic field. So according to epsilon equals BLV, the B is 0 at that location. Therefore, for F here, we're going to have no induced potential difference.